Good afternoon, Calculus. Hopefully it's Monday, April 29th, and you're going over this in class. Uh, this page should be in front of you right now, the Interval of Convergence page. This is something that was actually not tested on your final. I think there was maybe one multiple choice question, but there definitely wasn't on an FRQ. But was something that we're okay at when we took the unit summative on this one. But it's been a while, so we definitely need to review it here. Um, it was by design that you did the radius of convergence on Friday, because today interval of convergence is heavily based on radius of convergence. I want you to take about a minute, maybe only 40 seconds here. So whoever's proctoring right now, please pause the video and encourage students to read just these first two paragraphs here. Remind yourself of the difference between radius and interval, and then we'll talk about them very briefly. So pause, ready, go. Okay, I just wanted to highlight that your power series chart does have these things listed, and you can see examples of this. For radius of convergence, it says, maybe there is just a small section of the real numbers where your series converges, and we got to check endpoints. Maybe it converges everywhere. Maybe it only converges at one single point. Our interval of convergence is our goal for today. Essentially, you're going to do the radius and then check the endpoints. And that's about it. This mentions you use the ratio test or the root test. You could also use the geometric series test if it is in geometric series test form. Only if it's in geometric series test form. Essentially, ratio test is going to be your best friend. For the first section problem, you could use root test, but ratio test almost every time. So we're going to run through two examples together just to make sure we're on the same page. And I want you to be pretty precise in your notation and in your formatting, because we need to be clear which endpoints we're testing, what we get for each of those, and why they converge or diverge. I'll show you when we get there. So step one, we got to just do the ratio test on this series. So the limit as n approaches infinity. Ratio test, I'm going to ignore my alternator. That's the -1 part. And then I start with my x to the n plus 1 over n plus 1. And it would be divided by a sub n, but I'm going to multiply by my reciprocal here. So just flip it and write the standard form of a sub n here. So n on top, x to the n on the bottom. One thing does cancel here. So x to the n cancels. So we have the limit as n approaches infinity of x times n over n plus 1. And that's got to be less than 1 for this thing to converge. So based on our horizontal asymptote rules, essentially this says x has to be less than 1. You would get the absolute value here. But then based on that absolute value, you could say, okay, -1 less than x less than 1. That's considered the interior interval of convergence. So my radius of convergence is 1. My interior interval is from -1 to 1. But now I need to test endpoints. So here's where I've seen some not so great notation, and what I really want to encourage you to do is be clear about which endpoint you're testing, plug it in for x back into the original series, and then simplify enough that you can easily show or prove how it's converging or diverging. Here's what I mean. I'm going to plug in -1 and 1. And when I plug in -1, my series looks like this. The sum from 1 to infinity of -1 to the n minus 1 times 1 to the n over n. 1 to the n is just 1. So let's simplify this slightly to really prove that it is exactly a series that I know already converges. So I'm going to move that alternator up to the top. 1 to the n is just 1. And now we can recognize that this is actually the alternating harmonic. And so this is a known series. This is one we can reference. So we're going to say converges. It's the alternating harmonic series. And that's enough justification for us to be okay proving that side of it. And then let's plug in negative or positive 1, excuse me, for the other side, 1. We got the sum from 1 to infinity. The alternator's still out front. But now, oh goodness, I just plugged in 1, didn't I? Oh, Mr. Vulcan, you fool. Okay, well, let's switch this here. This is positive 1. And this one's negative 1. I think I did it right for 1. Yeah, that looks good. As long as I switch those, we're okay. Negative 1 looks like this. Negative 1 to the n, all over n. Now, this can be tricky because we have 2 alternators, and we need to check and see if it's still alternating or if it's no longer alternating. We got to combine our bases to check this. So our bases then would be negative 1 to the add exponents, right? So it's to the 2n minus 1 all over n. And now our question is, does that still alternate? So if I plug in 1, I get 1 as an exponent. Okay, so it's odd. If I plug in 2, I get 3 as an exponent. So it's still odd. If I plug in 3 for n, I get 5. Okay, so this numerator is negative 1 always to an odd degree, which means it's always negative 1. So I'm not even going to write that exponent. I'm just going to say this is negative 1 over n. This is not alternating. I could even factor out the negative and put it out front. This is just the negative harmonic series, the harmonic series flipped over the x-axis, which we know diverges. So we'd say, okay, this one diverges. It's the harmonic series. So I know when I plug in 1, my series converges. When I plug in negative 1, my series diverges. My final interval would be negative 1 less than x less than or equal to positive 1. There's my interval. And if we were asked for radius, we'd have that too. Find the radius, check both endpoints, plug it in, you write your final answer depending on converging or diverging. The next question's a little bit more gnarly, but you're definitely capable. Excuse me. So I did include a fact here. I added fun because I thought it was fun, but the source I got it from did not have fun listed for some reason. But there's definitely always one point where the series converges, and it's where my series is centered. So something always converges somewhere. So even if you think like, oh, this diverges everywhere, if you're getting down on yourself, stay positive. It always converges somewhere in the series. So we're going to do one more here. They actually, this example was saving you a little bit of time, but I do want you to try this one on your own first. So I'd encourage you, I want you to pause this video, proctor in class for probably 4 or 5 minutes. This is a tricky question. I want you all to try the radius of convergence, try and find the radius, and then actually go on and try and find the interval here. So take 4 or 5 minutes. Try this question. It is a little harder, but work with those around you to make sure that you've got your ratio set up correctly. Ready to go. All right, hopefully that went okay. I did go ahead, I solved several parts of this. So let's go ahead and check our work as we're going through here. If that something's not clicking, take a second after I kind of let you release to look over the key and see where Mr. Bolton came up with all this stuff. But I want to emphasize, this term is a sub n plus 1. So I plugged in n plus 1 for this thing everywhere. And then it would be a sub n plus 1 divided by a sub n. But I just went ahead and multiplied by the reciprocal. So this is 1 over a sub n. I just flipped it over. You can go straight to here. That's totally fine. But keep your limit notation. Keep your fractions looking good. I did simplify one step, and then it's necessary too. So on top, x to the n plus 1. On the bottom, x to the n. All those x's to the n's cancel. We're just left with x on top. And then we can use the opposite argument here. 3 to the n cancels. All that's left is a 3 on the bottom. And we can get to here, which now using our horizontal asymptote rules, it's the same degree on top and bottom. So x over 3 has to be our coefficient here. That's the thing that has to be less than 1. So there's our interior interval of convergence. It goes from negative 3 to 3. And now we got to check our endpoints. So this was the ratio part of it. This is what we did on Friday. Friday was my grandma's birthday. I'm pretty sure she turned 84. No, she turned 83. 83 years old. Wow. prime over life. I'm pretty sure 83 is prime. Now we got to check each endpoint. So -3 and 3, I've listed both of these here. I actually already plugged in each of these because almost every time something nice is going to happen or something to make your life way easier is going to happen. When I plugged in 3, the 3 to the n will both cancel. So the series actually looks like this, where it's the series from n equals 1 to infinity of 1 over n to the 3 halves. What argument could we use to say that the diverges? That's now a p-series. So it's a p-series test where the p, the power on that n, is greater than 1. And since it's greater than 1, this converges. So our argument here does need to be converges by p-series test since 3 halves is greater than 1. Make sure we're clear about why it converges and why it diverges. And if we're not, then try your best to simplify until you recognize something, right? The next one here, it's not quite as obvious, but we can actually rewrite -3 to the n as -1 to the n and 3 to the n. Remember, if I got the same exponent, I can multiply things to combine them in that fraction, which is nice because now those 3 to the n's cancel. And on top, I just have this alternator. This converged already, and now if it's alternating, it still converges. So this is an alternating p-series, which doesn't really matter. You can just say it still converges by p-series test, since that 3 halves is greater than 1. If you wanted to use alternating series test, you could. If you wanted to say something about absolute convergence, you could. But I'm just going to say p-series test. So converges by p-series test. I guess for that matter, you could use integral test for both of these. No, you couldn't use integral test for this one, but you could have for the previous one. So both of these converge. So that means my interval, instead of being -3 less than x is less than 3, I'm just going to mention this as the interior. So that when I write my final answer, -3 is less than or equal to x, which is less than or equal to 3, because both endpoints converged when I plugged their x values back into my series. These problems take a lot of work, and often on the AP test, they're 5 points on your series question. I've seen questions that, and you've seen questions, you've done a bunch of these now. The first 2 points are write the series. The next 5 points are do the interval of convergence, and then the last 2 points are do the alternating series error bound or something. So we've done error, we have written series, we talked about ratio test to find radius. Interval of convergence is a big item that's tested on the AP test. From here, I want you to go to your section. I haven't made the key yet, that's my empty key page for now. Go to your section and do these two. These are 2 multiple choice questions. So this can show up on free response or multiple choice. I know your box is going to be kind of small for these 2. Yeah, that's poor planning on my part, but do your best here. The top one, you could use geometric series test if you wanted. You could use root test if you wanted. We focused more on ratio test because it will work every time, but both methods work. On the second one, I would probably do ratio test. I can't think of an easy way to do root or geometric series. So keep that in mind. Try both of these. Use the key. Check your work. Good luck.